Right. Hi, everyone. It's my great pleasure today to have Nickolay Ivchenko with us. Nickolay is from KTH in Sweden, in Stockholm. He has done his PhD also in Sweden in 2002. Then he was a postdoc, first in the UK and then in the US, and returned to KTH since 2005. Has been assistant professor and I think since 2-3 years full-time professor now at KTH. He has led a lot of a number of summer rocket instruments, on which I also worked when I was at KTH during my postdoc. And more recently, he proposed an F mission for the last call from ESA, on which we are contributing with magnetometer and EPU. And his lab is also contributing to our own F mission proposal from Luca. So there is an interaction. And yeah, today he's going to talk about sounding rockets and small satellite at KTH. And the floor is yours.
Okay, thank you very much, Gabriel, and thank you for inviting me here. It's a pleasure to be here. It's my first time in Graz. It's very nice to see the facilities where our colleagues work, because we have had a long collaboration between KTH and Graz, I believe many of you are aware. So just jumping in here, I will talk about multiple things. We will see how time goes. Maybe I'll have to skip some of the stuff. I'll introduce briefly with KTH general information, and then talk about some of the things I've been involved with, which is rocket experiments, both student rocket experiments, but also research rocket experiments, and then we'll go into satellites. But first about KTH. So KTH stands for Royal Institute of Technology, Kungliga Tekniska Högskolan. It's the largest and oldest technical university in Sweden. We provide about 1/3 of engineering education capacity in Sweden. By European means, it's quite small. It's about 16,000 students, but it's research heavy. We have 2,000 PhD students, and that's how we want to see us. But with, yeah, it's a old campus from beginning of the 1900 in the quite central in Stockholm. Now with the global warming, we get less and less of snow, but yeah, hopefully will look like this in the winter. Right, looking closer, I'm from a group which is called Space and Plasma Physics. We have been organizationally part of different schools and departments. Now we are part of School of Engineering, Electrical Engineering, and Department of Electrical Engineering. After a year, shift of the year, it will change a little bit, so it will be electromagnetics and plasma physics, but that's kind of organizational things. And our group is quite small, but we've been involved in a number of missions of various scales and scopes. So we work on things ranging from ground-based observations, mostly optics and radars, integrated scatter radars, sounding rocket, small satellite, that's what I will be talking about today, but we also contribute to large missions such as ESA and advanced missions of cluster and MMS. And the future Auroral mission is something we are hoping for with the Andes proposal, which I will mention later. Yes, so this is just some example of what we do, and I would say it's a slightly different directions, what we do around the Earth and what we do going further away from Earth. What we want to look at around the Earth is the distributed measurements, because you have intrinsic spatial temporal ambiguity in satellite measurement. Even when you fly through something, whether it changed in time or you flew in something different, having multiple measurement points is a way to address it. And this is done in both large scale and small scale. So cluster mission is now finished, but it was a flagship of ESA where we had 4 satellites flying information and in the magnetosphere, contributing a lot to the magnetospheric research. NASA MMS is in a way a follow-up, doing similar things on much higher time resolution, addressing the electron scales in plasma. But we're also looking into nanosatellites and sounding rockets. And the way there was, for me, quite a lot with supervising the REXUS program experiments. REXUS stands for Rocket Experiment for University Students, and is a program run by European Space Agency and sponsored by DLR in Germany and Swedish National Space Agency in Sweden. Yeah, here you see some example. This is boom electronic board for electric field instrument built for MMS. So that's the kind of electronics we would build. That's even in the newspapers. That NASA takes help from Swedish. The other direction is on exploration in the solar system. And there, most of the things are done in big like large collaborations with agencies. So Rosetta was quite conspicuous and very successful mission where we had some hardware contribution. Betty Colombo is currently en route to Mercury. We have two electric field booms on the magnetospheric orbiter. So it's very exciting when it comes next, in about a year's time to Mercury and deploy it and start the mission in orbit. A solar orbiter is operating now. And of course, the big theme now in the coming years is Jupiter, because we have Juno there around, unfortunately, for the original mission design, they had a failure with the final rocket injection, so they get much longer rocket than in orbit than intended. But that way, it's also very much extended. So we get lots and lots of flybys, and there are two missions going there now. There is JUICE, where we are part of radiant plasma wave investigation led by Uppsala, and then there is also Europa Clipper with NASA, where we are part of the UDS, not with hardware, but on the science side. Right, so going closer to the topic of what I want to do today. So why sounding rockets? In the boundary between atmosphere and space. It's a collisional region in the what we call as lower thermosphere and ionosphere, where the ions are to a degree collisionally coupled to neutrals, whereas electrons are mostly magnetized. It's a very rich region because it is exposed both to plasma processes, but also the neutral processes for the atmosphere. And it is very difficult to have in situ measure. It's too high for balloons and it's too low for satellites, although we had some work towards deeper missions, but unfortunately it has not yet realized. Yeah, but also it's kind of close at reach to do multi-point measurements. So that's what I was working with students and as a research. And then also you don't have a long mission, but you can try to catch the event you want. So you can launch at the predefined conditions. And much of development was done at KTH with rocket experiment university students. We run something like 12, 13 projects where I was involved in supervision of almost every of them. And it's students from different fields working together, and the project cycle is about 18 months, where we start from designer, experiment, build, and then hopefully fly it on a sounding rocket. I'll show you some examples of what the students have done. We also have a very good example in-house with a team supervised by Gabriel. Yeah, so why was I doing it? Of course, it's very cool to work with students, and it's very good education. I believe it's good to be doing things hands-on, and especially for engineering students. But the motivation for me was to test a lot of solutions on the technical side. Multi-scale structure requires multi-point measurements, and there is a huge potential for suborbital flights. First of all, the small-scale structure of the aurora is a topic which is not resolved, and I've been doing some research on that, and I see a lot of potential to do more. The launch range, test range allows very good and unique facilities because you launch on the land, so the payloads can be recovered, and that allows to do things a little bit simpler because you don't necessarily need to send down all the data. You can store the data on board and then go and retrieve the experiment, and that's what we have been doing. And it's a test bed for future satellite and rocket missions. Okay, so just showing some of the examples. So this is, well, all of experiments built at KTH had free-flying units, which means you have something being thrown out of the rocket, and then it does measurement, and then it lands on its own. In this case, we had an experiment to collect aerosols throughout the atmosphere. It was called RAIN. Don't ask me what it stands for, I would not remember. But yeah, you see camera recording through the side of the rocket, and you can see the free flyers ejected. There is panorama build down from here. You see the two free flyers. Yeah, finally the rocket is disarmed with a yo-yo mechanism for microgravity experiment. Yeah, but our free flyers are doing their job. So what was the job in this case was to collect the aerosols. We had about 1 kilogram free flyer, which consisted of the recovery system with a parachute to land and then recover. And then on the bottom was a turning wheel with a number of samples, which were exposed to the ram direction as the free flyer falls down. And then we looked in the electron microscope. So it was successful technically, everything worked nicely. We're still not super sure what we saw, but that's another story. Yeah, that's how the experiments look like. Typically, yeah, you would have either 14-inch or 17-inch or even larger payload. In Europe, the skin of the rocket, the cylinder, is a structural element, so that the screws going together mount to the next unit, and so on and so on. REXUS uses 14-inch module, so it's 356 millimeter diameter, and then you can build your experiment inside. In our case, this was 2 free flyers ejected by spring-loaded system in opposite directions, retained by a steel cable going around. So we could test a lot of solutions here. That's another experiment. Here you see the rocket fly. It's a single-stage improved Orion rocket, which reaches between 80 and 85 kilometers, depending on the payload. Muscat, multiple spheres for characterization of atmospheric temperature, is a falling sphere experiment. Essentially, if you drop a ball, because it's spherical, you know its drag parameters, you can reconstruct the trajectory. You can follow the trajectory and figure out the drag force. And knowing the drag force, you figure out the atmospheric density. And also you can catch the winds and so on. This was flown now for quite a few years back. You can see, you know, there are 4 spheres ejected from the rocket. You know, this is again looking to the side. And this is a panorama picture constructed. So you can see all 4 of them and 4 edges. That's how they look inside. So the spheres were glass fiber epoxy composites produced by Siemens themselves. Again, with an antenna system. There is a parachute under the cover. That's maybe people interested in electronics and data system would appreciate this. I don't have time to spend on this, but mostly we've been working with field programmable gate arrays for data collection and storing everything into memory. Yeah, the cool thing here, a bit on the antenna side, we didn't go there much more. There is a single antenna for GPS reception and the satellite modem transmission. The satellite we use is Global Star, and it's a close frequency to L1 of GPS, so we can use the same antenna with a hybrid coupler. Now we are using off-the-shelf antennas mostly, but it was nice development. You can see again the experiment, the 4 spheres quite tightly packed in and retained by cable going around. Yeah, it was launched. The 3 flyers were successfully ejected, recovered within 2 hours. You can see the landing track on the map with a characteristic wind spiral near the ground. And the experiment was so successful that we with rather limited change of hardware. There was some upgrade on the electronic side, but essentially very little upgrade on the ejection system. We have flown it for science several times now. That's more or less how the acceleration looks like. One of the challenges, of course, the sphere is spinning, so we need to work a little bit with the rigid body motion. But you can see the deceleration on the way up. Here is the apogee, here is acceleration down. It's space just for visibility of the spheres. Yeah, here is the re-entry, but that becomes a little bit less interesting. So the most interesting part is, of course, the high altitude portion of the winds. Yes, now so we come to the science experiment. And the first scientific mission we had is Spider. Here we wanted to use multi-point measurements of electrical magnetic field and plasma in the region to address the multi-scale structure and Farley-Buneman instability and turbulence. So the Farley-Buneman instability develops when you have strong electric field in the E region, because the ions are coupled to the neutrals collisionally, but the electrons are drifting across the drift. We have relative perpendicular to magnetic drift, which develops into electrostatic waves, and then they develop non-linearly into instability. So the target altitude is where you have the decoupling of ions and electrons. And that's about 95 to 150 kilometers. Yeah, that's what they said, more or less. And that leads to electron heating. I don't know if I have time to spend here, but there is a number of interesting phenomena. You could have anomalous Pedersen current closure in the lower part of the E region, whereas normally you would have it closing higher up. That can lead to energy deposition, low down, and so on. Yeah, we saw things with ice cut in preparation. So what you see here is a time history of line of sight parameters in the ionosphere measured. So you have altitude here, and the parameters are the electron concentration, ion temperature, and electron temperature. And then what you can see here, okay, there is an auroral arc producing ionization in the E region, and just at the boundary of it, you have very strong electron heating here, and then the ion heating is slightly higher up. So that's an example of Farley-Buneman instability. And now we would measure it. Yeah, we have 3 flyers with electric field for probes for electric field, magnetomes for probes, flux gate magnetometer. There's a magnetometer, there's electronics for data connection. And we have the GPS raw signal logger for reconstruction of trajectory. And the payload is kind of modular stacked. So this is the bottom module. The middle module is the probe deployment unit. So you see the probes here. And this is a drum where the 50 micron wires connected to the probe is turned. And it turns 3 turns or 5 turns, deploying it up to 2 meters. Yeah. When we had this first flight, Swedish television thought it was cool, and they put someone to make the video, which kind of explains what happens. It's not fully correct, but yeah. So the 3 flyers eject, and then they deploy the probes and measure in multiple points. Here we launched it in 16, and was recovered. It looks like this at recovery. Now this, we launched it into. What we wanted to see is a pre-breakup stable arc, so that we have nice behaved configuration and the turbulence, hopefully. Unfortunately, or maybe interestingly for other reasons, we launched in something which looks more like westward traveling surge, so very dynamic aurora. And this is just the time scale of the flight. So you can see here the position of 2 free flyers, and then the aurora developing this time. Yeah. There were some concerns with different kinds. I'll mention some of them, but we were also able to reconstruct the plasma parameters. Gabriel actually was working on this. So this is the density and electron temperature from 2 flyers flying side by side. We didn't see Farley-Buneman instability, probably because the conductivity was very high and the electric field was low. This is a comparison of plasma parameters. For this, I can refer to Gabriel's paper. Some of the concerns, well, we want these cakes, the free flyers, to spin in a flat spin, but as they come out of the rocket, they wobble a little bit. So what you can see here is ejection of the free flyer, and you have the green curve shows the spin axis component of the rotation, angular velocity, and the blue and red show the perpendicular one. So what you see is, okay, here is ejected from the rocket, and then we have some wobbling, and that's not very good because it kind of affects the deployment of the another point which we were not very successful with, or not. We wanted to have a apogee around 120 kilometers, so stay most of the time in the region of interest. But you can notice here, the rocket went almost to 140. So we switched by very quickly through the region of interest, spending not so much time there. Now the flat spin, and then there was a small concern with the recovery system. So we turned back to students, and there was another team of students which worked on the wobbling control. They inherited the hardware, and they looked at how to implement a reaction wheel to control the wobbling. And this is a demonstration they did. So it's suspended on a string in the middle, and I will show in a moment how the system looks. But what you can compare, this is two different experiments. So first they introduce the solvent, then they amplify it, and then they leave one of them just to dampen naturally, whereas the other one goes into active dewobbling. And the video works also on Zoom, and you can see that the dewobbling kind of has some effect. Okay. And this is the data of the same kind. So this is the spin axis angular velocity component, and these are two perpendicular ones. No, these are two separate experiments, yeah? But these falls onto each other perfectly. And then the blue one is the one with the wobbling, the red one is so this was looking very good. They also did the deployment of the boom. I'm mostly showing it just to show what it looks like. So we have a small spin table, and then the spheres are coming out now, and that's what we want to achieve. So we have the spheres stretched out in the steel plane, and we're measuring the potential difference between the spheres or the currents to the probes. Yeah, we were very happy at this point. Students were super happy, but then they realized they don't have a way to stop it. So it was really interesting. Yeah, they came to launch, and I'm showing quite a few launches here. You can see both of them there. Unfortunately, this whole flight was a failure because of our experiment. So the hatch retention slipped. The hatch came out too early. There was too much drag during the propelled part of the trajectory, so the payload broke apart. Big mess. So this was not good. So the experiment, which was perfect, unfortunately did not qualify. Now, okay. Well, we came, as we didn't catch the fallig on the first flight, we went back to the funding agencies that we want to try again. So Spider 2, we added a little bit more payload to the main rocket. So this time we have the 3 flyers, not 10 of them, but 8 of them. You can see the 3 flyers. We added the photometer and ion probes. Actually, the Faraday rotation experiment here goes back to Martin Friedrich, who you very well know, I hope, and now is kind of managed by EIP Königsborn. And and we had a own electron probe on the main one. So 8, 3 flyers for electric field line probes and magnetometer, and the falling spheres. Again, we flew here. Well, the target was again Farley-Buneman instability. Yeah, here you can see the nose cone assembly. So this would sit at the top of the rocket. You have the photometer in the middle, looking forward. You have the ion probe, the continuous board. You have the Faraday rotation antennas, yeah, and the umbrella of the electron probe. Yeah, and my PhD student made a more understandable diagram of this. Yeah, we did small changes in our probes. So we changed the alignment probes from spherical to cylindrical. For a number of interpretation reasons, we did small update mechanically here. And this is the reaction wheel due to the wobbling mechanism of the Wolf experiment. Yeah, the flight was good. Falling spheres worked nicely. So it's based on the Muscat, and we flew it another one, another time on another experiment in 16. Here you see the very raw data. So you have the altitude here, and this is the logarithm of acceleration. And of course, the top of the trajectory, the drag is very small, so the acceleration is small, and then as you go down, the air is thicker. So this is what the one you would be inverting to get the density profile and temperature profile, but also you can see very deep. That's an indication of a wind in the mesosphere, but there is more work ongoing there. We have not had too much resources for that part of analysis. Yeah. Then, okay, that's how it looks at test range when things are put together. It's a launch, recovery. Some of the things were found directly. Some of the things had to wait until the summer to be found, but the data was still there. And a short comment. So we were getting, with some rockets, as I said, it's a very good opportunity because you can choose what you launch to. This is true, but not fully true, because sometimes you wait and wait and wait, and what you want to achieve does not happen. Then you need to change, to choose very difficult decisions. And the decision here was on the last night, essentially, of the possible window to launch or not to launch. And we had a couple of substorms happening, but they were all too far north, not coming to Kiruna. And in the end, there was another one, but we saw, okay, we are too far down on the morning side. It's not discrete aurora, it's pulsating aurora. So we launched into pulsating aurora. What you have here is a kilogram from Kiruna. This is 1 hour. This is the cut through meridian, optical intensity, and you see this vertical stripe, that's pulsation. So pulsating aurora comes on and off with periods of a few seconds. Yeah, we got the data. Everything is yeah, will work more or less nicely. So you can see here the photometer data, the electron probe, the electric field. Yeah, zooming in on photometer here. Now, the photometer is provided by our colleagues from Meteorological Institute of Stockholm University, who do a lot of research on upper atmosphere. And the way they interpret the vertical profile from the photometer is you're looking up, so you essentially see all the emission above you. And then as you go higher and higher, you would see less and less. So you take the profile and differentiate, and then you get the vertical profile of emission rate. And that normally works. And they looked here and said, no, this is not good. This is too noisy. Well, it's not noisy because this assumption, looking up and then differentiating, assumes that the emission stays stationary, which it does not. We know it's pulsating aurora. So this is actually the pulsations. Yeah. And we looked with density data and electric field. So the density is now, yeah, Langmuir probe analysis is now published with my PhD student. Electric field we're still working on. You have sweeps. So on the Langmuir probe, you can change the voltage and measure the current, and you get the diode-like characteristic, which you feed with parameters. Again, you can catch Gabriel all about it. Yeah, and you can reconstruct the electron concentration and the electron temperature. So, yeah, this is a diagram of the flight. We fly through ionization region in the E region, and pass it twice. I think this is actually maybe not. Yeah, but okay. So what we do is we measure the electric field, and then on the Langmuir probes we make sweeps, in rotating pattern, changing their voltage with respect to the free flyer, and then we get the characteristic, which you feed with a theoretical formula. You reconstruct the parameters, and then you get the altitude profiles of density, which changes with pulsations, and that's the first publication. A little bit sidetrack here on another experiment we did, it was called Prime, where we wanted to do this Langmuir probes on an even smaller payload. And the idea there, okay, this is from their proposal. Yeah, there is a company in Netherlands who make small rockets. So this small rocket, DART, as it's called, is a bit of a successor of earlier Super Loki or Viper rockets, which were used for meteorological research, but they're now not made anymore since 30 years or so. So this is kind of a new version of it, and they find niche which they want to go. It's very nice. It's a single stage rocket which can go up to 120 kilometers, they say, and the aerodynamically shaped DART can carry the payload there. The problem is the payload is very funny shaped. It's essentially a very small arrow or dart. So if you want to have something inside, it has to have 30 millimeter outer diameter. But hopefully the rocket will be useful. Now, from the proposal of this time, the idea was, okay, the DART will go in November 2019, and we want to make a demonstration of the payload on the REXUS experiment. So the students got to build the payload, which was hopefully going to fly on November 19. Yeah, so that's how the DART rocket looks like in real life. That's how the payload looks like. And on the rocket of REXUS, so with 14-inch payload, you remember, yeah, they were stacked sideways, ejected on the rocket. That's the payload you can see here. And here there are the deployable Langmuir probes. It flew, yeah, and landed, so it was quite okay. We got some data. Now, next slide had to wait until 2024. Well, there was Corona in between, there were lots of things in between, and we launched it, but it was not very successful because they are openly performed, but they're working on it. Right, okay, so now we are coming to the next research rockets, and these are SYSTER and Brur, and those were proposed more or less at the same time. So SYSTER is Swedish for sister, and Brur is Swedish for brother, and they're closely related in a way. So both of them looking at the transition from atmosphere to space and small space structures. So looking at the region in the atmosphere. So in SYSTER, we target the Joule heating altitude profile, and we want to measure it through all the parameters for both plasma, fields, and neutral component, neutral winds. And Brur focuses more on the neutral winds and dielectrics in the atmosphere. So Brur is an active experiment. Going back to barium releases. Many of you would remember the active experiments were done ages ago, but they're now going through revival. The US is doing them, but Sweden has no capability to do them. So they were proposed at the same time because of a number of programmatic reasons. Well, we wanted even to go together, but we realized very quickly that it's not possible because we have quite different requirements. And Brur was considered simpler and cheaper, and it was realized first. So I'll tell you a little bit about that. Barium release optical radio experiment. And these are the targets looking essentially One makes active experiment by releasing barium. Part of it gets ionized, part of it is neutral, and both of them scatter sunlight, which you can observe from the graph. And this is done with Clemson University. We actually had no part in Grove. I'm just telling you because it's in Sweden. Okay. Do you think it might work? If not.
You will open another.
Okay. Well, I recommend you to follow the link and the review. It's a very nice video. So you have the rockets flying up and releasing barium clouds. Part gets ionized and drifts with the ions. The other expands with the neutrals. So it was successful, launched in 2023. And with SYSTER, we are still preparing. So we hopefully by February 2026. So now it's quite busy times. So for our part, again, yeah, this Muscat spheres, spider free flyers for multi-point measurements. And then you see we have a bunch of other experiments. In particular, we have a package from the US, and the central parts in this package are the neutral wind experiments. We have two neutral wind experiments from the University of Texas, Dallas cross-wind track sensor, and the ionization gauges from University of New Hampshire. So we measure the winds in a slightly different way. We have high energy and auroral energy electrons, and then we have another plasma sounder, and we have more instruments from Europe and Canada. So it's really a comprehensive payload to measure everything about plasma and neutrals and fields. For our parts, we will also have the electric field instrument with rigid booms on the main payload. Right. Another Swedish rocket which just launched is called Origin. And we have the falling spheres there. But the main purpose of this rocket is looking at the oxygen emissions and the pathways of excitation of oxygen. They have a whole bunch of photometers looking out in different wavelengths, and they have the relation between different spectral transitions of atomic oxygen and molecular oxygen and how this is excited in night glow and to a smaller extent in the aurora. Right, so this was one launch was in February. Unfortunately, there was an issue on the rocket side, so it did not perform nominally. It did not reach the intended apogee, but then we launched a couple of weeks ago, which was successful. Right, so aurora and the recent focus on aurora. People have worked on aurora for a very long time, but you still discover new things. And this is just an example. One thing which came up in the last few years was something Steve, which is a very interesting phenomenon. So it's an emission which doesn't seem to be auroral in nature, in the sense that it does not follow the spectrum of the typical emission, but it looks more like it has a continuum. Or in the subaraural region, and what we recognize now more and more that it's related to subaraural ion drifts. And the emissions are probably generated locally rather than excited by precipitating electrons. So that's received quite a lot of attention. Another small phenomenon is fractured and fragmented auroral emissions, which you can see here. Sometimes they're even related to STEER, but this again on scale of several kilometers. Also, there is evidence pointing to local generations in the E region rather than imposed from above. Another thing from citizen science was so-called dune aurora. Mina Palmroth has published it a couple of years ago, looking at diffuse auroral sheet. Seems to be modulated by these regions. And there are ideas, maybe this is related to gravity waves, atmospheric gravity waves. So, and this is all kind of past several years. So there is a lot of things going on there. We want to do stuff. Right, now I would like to shift a little bit more into satellites and to go back into history. That Sweden was very successful with small satellites early on. We had the Viking, well, it was not super small, but by that time it was still quite innovative. Auroral satellite, Freya, done a lot of things on the Aurora. When I came to do my PhD in Stockholm, I was working with ÖAW-Institut, which was the size of the old fashioned geograph projector. And the last small satellite was Odin, which is a combined radio astronomy and atmospheric satellite looking at the water emissions. And it's actually operational still. It's been up since 2001. Should re-enter maybe next year. So there is a bet when it will re-enter. Right, and then after that, there was a political decision in Sweden taken on the agency level that most focus should be put on the large agency missions like ESA, NASA, JAXA, and there was barely anything done on the national side. Not Sunny rockets so much, not small satellites. But a few years back, this has reverted, and there is a realization that we can do things even with small satellites, which do not necessarily require the agency like ESA scale, and this could be useful both for research but also for development nationally. And there was an opening for small satellite program, and the first mission to be realized there in France. Yeah, Mesospheric, Airglow, Aerosol, Tomography and Spectroscopy, and that was the mission we worked on. Yeah. So what is the point here? The point is to see the waves in the atmosphere. We have gravity waves in the atmosphere generated by orographic sources like the wind blowing over mountains, large weather systems, and so on and so on. And as the atmospheric gravity waves propagate in the atmosphere, they transfer energy and momentum, depositing in different altitudes. So they facilitate cross layer coupling, contribute to driving of the global atmospheric circulation. And there are lots of things to be learned about them. And in this mission, we want to study them, or, well, that's the main goal of the mission. And the way to do it is to look at how we can see them. And we cannot see the waves directly, but we can use other optical phenomena which are modulated. And those are the Airglow, in this case from the atmospheric band of molecular oxygen. It's not visible from the ground because it's absorbed in the molecular oxygen, but you can do it from space, or noctilucent cloud. Noctilucent clouds are the mesospheric clouds at altitudes about 80 kilometers, so very thin ice crystals. In both of them, as the wave propagates through and creates compressions and rarefactions, the temperature is changed, so you get different emissions intensities, or you get different conditions for condensation. And you can see these noctilucent clouds, well, they're not shining in the night, other than it's a scattered sunlight. So they observed in the summer. I don't know if you can see them here much, but in Stockholm, it's quite common in the summer. You have dark on the ground, twilight, and then on the altitude of the clouds at 80 kilometers, you have solar illumination. They scatter, and you can see the wavy structure in the silverish. And they're very beautiful. Not as beautiful as now. Right. Okay. Tomography simply means that we want to look at them from different directions and reconstruct how the emission comes.
It's now 15, so 45.
Yes, thank you. Yes. So, what else? Yeah, Odin actually did a little bit of that. It has a scanning photometer. So it was scanning in different view directions, and then you, assuming that the thing does not change, you can sort of reconstruct a single car. And what we want to do here is do it in 3D with imaging. Okay. Spectroscopy Well, we have different channels. Again, this is from Udin. Looking at the noctilus and clouds, you can do it in the UV channel, in the UV range, and looking at different wavelengths, you get different intensity depending on the size of the particles. So the scattering of the particles will be more or less bluish depending on their radius, and then you can reconstruct the size of the particles. Looking at the spectrum of atmospheric band, so here you see the spectrum of atmospheric band, wavelengths in the near infrared, and the shape of it is a rotational band. Well, rotation, the structure of the band depends on the temperature, and the rotational temperature is closely coupled to kinetic temperature. So the higher it goes, the wider gets the spectrum. And looking at the spectral shape, one can get the temperature. And that's very good in the Airglow layer, and you can do mapping of the temperature. Again, this is from Udin, and you can reconstruct how the temperature changes. So, MATS is led by Stockholm University. Airglow and Linda are the principal investigators, and the payload consortium included Chalmers and Omnisis. Now it's part of the OAC Clyde and KTH. And the InnoSat platform was developed by OHB Sweden and the AC Microtech, or now it's OAC Clyde in Uppsala and Stockholm, and funded by Swedish National Space Agency. Right. What we want to see is the noctilus and clouds. This is an image from the ISS, and the MATS field of view is very narrow in altitude, but 250 kilometers in width, part of the horizon, or the limb as we refer to it. Okay, I will probably need to skip this, but we measure, we take the mid images in 6 channels, 4 infrared and 2 ultraviolet. The 2 UV channels give us the size of the particles and the noctilus and clouds. The infrared ones give us the temperature. And of course, the intensity of the Airglow. Now, getting it a little bit more technical, what we did at KTH was a CCD readout electronics. So we have the CCD from E to V Marconi, or now Teledyne, and then we have the onboard payload computer, Omnisis, and we were in. So lots of abbreviations, CCD readout box essentially. That's how it ended up looking. This is the power distribution board. For CCDs, you need to produce a lot of bias voltages and clocks at strange voltages and so on, and then to digitize the signal. The analog part has to be close to the detector. So this is the analog part, and we have essentially an FPGA here forming the image, and that is sent back to the OBC. That's how it looks like in the engineering model. We have the volt with OBC, 2 of our distribution board, and that's kind of one of the digital channels, another one. So in total, we have 7 of them, 6 limb looking, and 1 looking down is the nadir. That's more or less indicates MATS going over the orbit. We take images downward and we take images to the side, 2 UV channels and 4 infrared channels. Yeah, let's see if this video plays. Yeah, this shows one of the channels, in this case UV2. So we're looking at the noctilus and clouds. You see here lines of indicated altitude, and then in the bottom one you see the satellite position and the tangent point position. So the point where the image is taken. And if this play, yeah, okay. So you can see the layer of noctilus and clouds coming up and down as we fly over it. So that is again. There is a satellite, it looks at the green point here, and as we cross over Antarctica, we cross the layers. And that could be reconstructed in 3D and get the wave vectors and the distribution of the weights. that's what people on the atmospheric side doing. We, of course, were super interested to see, can we see the aurora with it? And we can. And that's your Airglow layer. And as we fly by, this is the aurora above the layer. So looking at the bottom, this is what happens to the satellite. Looks the Airglow layer at all times. And as it moves through, we have aurora above. Then it first comes from below, and then when we look tangentially at it, it appears above the layer, and as you pass over, it goes down again. You get this characteristic feature in the kilogram, which is the altitude cut here and the function of time. So we could look at it, and we had a master student go through it and do some statistics. And now this is actually published a couple of weeks ago. The distribution of auroral crosses. What we saw. Okay. Again, I revert to Judith's paper on this, and maybe two last points I would like to make. Two other missions where we involved a little bit. Well, a little bit in this one and pretty much so in the next one. So this Romeo mission is run by University of Stuttgart, who we have close collaboration with. And it stands for Research and Observation in Medium Earth Orbit. It's ERS in Stuttgart, who are essentially testing lots of new technology systems, but also have the payloads. The key point here is they will go into SSO, LEO, 400 kilometers, and they will use a novel water propulsion system to break the water into hydrogen and oxygen and then burn it. So electrolyzer and a big tank, and the intention is to raise the apogee to 2,500 kilometers, going into medium Earth orbit, and then do some observation there, and that's it. So the plan is, well, what they say, the plan is to launch it in 2026 by the end of the year, but that goes through the IOD program with European Space Agency EU. So maybe it's. I think it might be a little bit later. Okay, there are some payloads there, and our part, okay, the payload there, some are technological, water propulsion system. They make the avionics themselves. There are some solar cell experiments, but then on the science side, there is Earthshine telescope. So that's looking at the albedo of the Earth in a global sense. That's more related to climate than to us. But then on the space weather side, there is a mini radiation monitor looking at high energy particles and even higher particle energy instrument from another German place. But we have the Langmuir probes from KTH. We are developing, and we want to study the evolution of the atmosphere in response to space weather effects, and maybe even coupling it to higher energy particles, how the radiation belts are affected, but also to see if this water propulsion is noticeable in plasma. What we're trying to do here is we have our system in COTS, with commercial component, which is built on the Pro A63 FPGA, which you're using also here, and STM32 microcontroller. And also we are looking and working now on a redundant system or alternative system, which would be using the NanoX for energy medium FPGA combining everything. So that's work in progress. We'll have to update in a year. Yeah, now the final point of my talk, and that's the F+ candidate. So we proposed mission called Hannes. Hannes Alvén was the founder of our group. And the idea here is we want to look at the small-scale dynamic aurora, resolving the temporal and spatial scales in it by using twin satellites to study auroral morphology, imaging, electron precipitation, and electromagnetic environment. Now that's just to sell in that small-scale structure in aurora is beautiful, complicated, and not very well understood. You see structures on the scales of kilometer and subkilometer, which are evolving in time scales of seconds. And as you fly through with a satellite, yeah, we know a lot from Freya and FAST and so on. Then you have a single picture, a single moment picture. Yeah? Ray May from Japan did a great job by imaging the footprint of where a magnetic field goes into the ionosphere, so showing the aurora from above and studying the electron precipitation which creates the aurora. Now we want to go one step more. So both of these are Ray and FAST and Ray May are single point measurements. We want to do a constellation. ESA's first constellation was Swarm, which was Earth's observer, very good, studied magnetic field ion drift, but nothing with aurora, no particles, no imager. And we want to do a combination of all of it. So that's instrumentation. We can discuss it, those who are interested. The key mission, yeah, essentially we can also jump it over. We would combine it with new development as a ASCAT 3D. That's picture I took, so it does exist. It will start running anytime. And that's my last picture. So twin satellites following each other with a small separation will help us understand whether we're seeing the temporal structure or station structure or some kind of revolution. Thank you very much. That's what I have.
Thank you very much. And it's almost 2 o'clock, so we can run a few questions, and people can stay, of course, but if you have to run, you can ask the question and then leave.
I have a question about, first of all, thank you, a nice presentation. I have a question about multi-point measurements. What could you learn from multi-point measurements, which was something extra relative to single point measurements about turbulence?
Okay, specifically of turbulence or in general?
Specifically turbulence, but if you can add something else, I am open to listen.
Yes. Okay, so that's a very good point. I would probably start with something else, and then we can go back a little bit to turbulence. So what we want to achieve in Anna's mission is simply to see when we fly through the same kind of point, and we see it evolving in the imager, so we see how the aurora evolves, how the electromagnetic signatures are related. So there is an understanding of many parts of the small-scale dynamic aurora being related to dispersive Latvian waves, and there is a lot of modeling. Modeling goes in slightly different directions. Some people would call this turbulence. I would be a bit cautious because it's complicated. It's not necessarily turbulence. It's more like a 3D complex structure with waves interfering and so on. But some of them are nonlinear, but I'm not sure if it's fully developed turbulence. So yes, I actually brought it up as one of the questions. So how will you address turbulence? And I think with a small scale dynamic aurora, we probably need to address the elements of the turbulence first before we can address turbulence. And with 2 points, it could be challenging. Yeah. Now going to back to the spider rocket. So, it would be nice to show you. Yeah, that's what we saw. Well, that's yeah. Well, we didn't catch fallig turbulence. The idea though would be that we expect to see in the E region, when we have strong electric field, we expect to see the Farley-Bunneman instability developing into, it's electrostatic instability, and it develops into density variations on different scales, which also has a dependence on there is a time evolution. There are numerical models of the turbulence, how the spectrum looks like, but also how the waveform looks like. And also there is an altitude dependence. What you typically see from that is there have been a few rocket flights which had a single point measurements, and that's of course limited in the interpretation because you need to assume that what you fly through is equivalent, the time and space equivalence. Yeah. but the other way of seeing it is with the radar. And with the radar, you see only one wavelength. So you pick up one K vector, you can see time evolution, but that's it. You don't see the development of it. So that was a bit the idea that we capture with the rocket the different scales. I wish I could tell you more with the results, but we don't have results on that part.
Any last question?
I have one.
Yeah.
You have, do I need this?
No, you will wait for everyone, maybe from the back.
Maybe for Zoom, yes.
We have, so, you flew through the noctilucent clouds, or you want to fly through noctilucent clouds. My question is quite general, so you always have to fly to some cloud boundary at some point, don't you? So, and if you do you see a change in electric field as you do?
Okay, which one are you referring to? So
It doesn't matter. I'm really asking for if you ever have seen the electric field measure, the measured electric field changing as you cross the cloud boundary.
Okay, the pictures I showed about noctilucent clouds, they were more related to MATS, and MATS is a limb imager satellite, so it's always above, it does not fly through, it's only doing imaging. But I guess you're more relating to the rocket flights. And there are people in like Kullensborn, for example, in the US, who flew rockets specifically into clouds, and they did a study on that. And there are lots of interesting phenomena which are happening there. In particular, you would get negative charges, you would get the cloud particles are charged. There is a lot of work on the role of meteoric smoke for the condensation of the ice. I would say this is not really my field, so I would not tell you very much about, but people are doing it. People are even hitting the noctilucent clouds with a heater experiment with radio waves and seeing how the charge attachment, detachment changes, and there is a lot of plasma physics there. My interest specifically is more on the auroral side. So the rockets we were doing are auroral, and we don't very much look below, let's say, 95 kilometers where the clouds are. Yeah, and then I don't think the winter is a place in clouds anyway. So, yeah. But it's an interesting question. There is lots of plasma physics.
Thank you. So, thank you very much. If you have more questions, we can.
Yes, thank you.
Well, thank you for coming to the seminar.